Hi folks, and welcome to the screencast on reaction mechanisms. Before we get into mechanisms, let's review rate laws a little bit. And one of the tenets that you've learned about rate laws is that the rate law expression does not usually match up with the coefficients of a balanced equation. You should know by now that when you come up with a rate law, such as rate equals k times a to the first, b to the second, it doesn't necessarily mean that a has a coefficient of 1 and b has a coefficient of 2. Rather, those numbers are determined experimentally. Now why is it? Why don't they match up? And that's because the reaction usually does not happen in one step. Here's an example. 2 NO2s plus F2 makes 2 FNO2s. It looks like a pretty straightforward synthesis reaction. You got 2 molecules of NO2 combining with an F2 to make these 2 new molecules of product. But when you look at it molecularly, it's a bit more complex than that, and as it turns out, improbable. It's probably not how this reaction happens. Just to read the caption here of this diagram, it's highly improbable that the 3 molecules will all collide with each other at the same time with the correct geometry, and in this case the appropriate amount of energy, activation energy. Having all of those ducts kind of lined up in that proper row, it's probably not going to happen when 3 molecules of these 3 just happen to be close to one another and colliding, and in this case reacting with one another. In reality, a reaction takes place in a series of steps called a reaction mechanism. And it's just that. It's a series of elementary steps by which a chemical reaction occurs. The reaction probably occurs like this. You got step 1, which is NO2 plus F2 makes FNO2s plus F. And then step 2, this new F product from step 1, reacts with NO2 to make FNO2. You'll notice if you take the 2 steps and add them together via Hess's law, the way that we learned not too long ago, you'll get the same overall equation as the one that we presented originally. Here's a graphic representation of this model now. This is probably how the reaction occurs for step 1. It's reasonable to think that the NO2 molecule hits an F2 molecule, resulting in FNO2 and an intermediate F. That intermediate doesn't last very long in step 2 right there. It reacts with another NO2 molecule and will make a new FNO2 product. It gets cut off there a little bit at the bottom, but it pretty much just says that these 2 equations will add up to give you that same overall equation that we started with here at the beginning of the screencast. Now, characteristics about a reaction mechanism that you ought to know. Number 1 has already been mentioned. The elementary steps should add up to give you the same overall balanced equation that you started with. And number 2, the mechanism must agree with the experimentally determined rate law. We're going to learn in a few minutes that you can use a mechanism to determine the rate law of an overall reaction. And that should match up and sync up with the same exact rate law that one would get if you were to run that experiment on lab setting, collect data, and then determine what the rate law is. Now you should know that every mechanism has one slow step, and that slow step is the rate determining step. In any multi-step reaction, or any multi-step process for that matter, the slowest step is always a step that will determine the rate of the entire process. There's a lot of good analogies and examples. The one I like the most is about funnels. If you take 2 funnels and you stack them, you put one into the other, like A into B, or B into A. It turns out that the thought experiment that I give students is, what if you have a glass of water and you want to pour it into a funnel? You pour it into A, which then goes into B. Or you pour it into B, which then goes into A. Which setup is going to go faster or slower? A into B, B into A. The answer, of course, is that neither step is going to be faster than the other, because this funnel A right there, is going to be determining how fast or how slow this entire process happens. It doesn't matter if it's first, it doesn't matter if it's second. That funnel A is going to determine how fast that little pouring assembly process is going to go, just because of the fact that it's much smaller than funnel B in terms of diameter, both at the top and at the very bottom of the funnel. And again, the experimental rate law must agree with the rate determining step. So make sure you have that clearly written out in your notes. Now, one possible problem that you might get is to identify the rate determining step. So here's a reaction that's already provided. There's the experimental rate law determined experimentally. Which step in the reaction mechanism is the rate determining or slowest step? Let me pull up the mechanism. There it is right there. So this is the proposed mechanism for this overall reaction. You'll notice they add up to the overall equation, which is what we expect. Now to figure out which one of these 2 steps is the slowest step, what you need to do is you need to write out the rate law for each step. And the way that you can do that now is you can, and you should, and you need to, use the coefficients of the reactants as your orders. So for example, we've got H2 and we've got NO. That's a 1, that's a 2. So my rate law for this first step should be H2 to the first, NO to the second. There it is. And for the second step, that pops up as well. N2O is to the first, H2 is to the first per the elementary step. So in this case, and this kind of contradicts what I said earlier about coefficients not matching up with orders. They do match up in an elementary step because there's no step that's more basic than this step within this mechanism. So whatever the coefficients are will be the orders of those substances in those rate laws. So here's kind of rate law for step 1, rate law for step 2. One of these should match up with the experimental rate law, and we'll see that this first one does right there. So what that tells us is, since this rate law is the same as the rate law that we get experimentally, this first step right here must be the rate determining step. It must be the slow step of the two. Here's just a summary of that. Rate laws for elementary steps can be determined based on their coefficients. So we've got a to the first for the first one right here. This would be a to the second, a to the first, b to the first, a to the second, b to the first. We see that right there. Originally I had written rate law for the elementary step, but it turns out that if it's the elementary, or if it's the slowest step, then that rate law will be the rate law for the entire reaction as well. You should also know that mechanisms contain some substances that do not appear in the overall equation, and those are intermediates and catalysts. The definitions are listed here. I'll leave those for you to read, but the key point there that I want to make is that intermediates first appear as a product, then they appear as a reactant, versus catalysts, which first appear as a reactant, then later they appear as a product. Here's an example. Here's an overall equation. What species in the reaction mechanism? In this case, are intermediates. Turns out there's just one. If you look at the two equations and add them together, you'll get the same overall equation that you see up top, but there's an extra substance in there that we don't find in the overall equation. And you might be able to spot it if you look. If you don't, there it is. It's N2O. N2O is going to be an intermediate. The reason, of course, is that it first appears as a product, right over here in step 1, and then later it appears as a reactant in the subsequent step, the next step. It's not found in the overall equation, so we call that an intermediate. Catalysts, I pretty much cut and paste that slide and then just changed a few things around. Which species in the reaction mechanism in this case are catalysts? And at a glance you'll see what the one thing that's different from the previous slide, and that is my addition here of carbon dioxide, CO2. First time you see it in step 1, you see it as the first substance. It's a reactant. Then later you see it as a product. It's technically, as far as catalysts go, not going to be involved in the equation or the overall reaction, and we call that a catalyst. Finally, identifying the rate determining step. For this reaction, determine the rate law based on the following proposed mechanism. Here's a fast step. Here's a slow step. So first off, you can do this on your own, and you should do this on your own. Write out what the rate laws are going to be for those two elementary steps. You should also double check that this mechanism, the two elementary steps, add up to give you that overall equation up top. You'll see that they do. Here are the two rate laws for the steps. Rate for the first one is equal to K times NO to the second. The second one, rate equals K times N2O2 to the first, O2 to the first. You'll notice that I tell you that this is the slow step, and you'll be given this information with these types of problems. So this rate law must be the rate law for this overall equation. But there's a problem. And that problem is that there's an intermediate there, N2O2. You can't have a substance in your overall rate law that does not appear in your overall equation here. There's no N2O2 anywhere to be found there, so we can't be using that as a claim for what our rate law is going to be. So what do you do? Now this step gets a little complicated, so I'll try to go through this a little slower than usual, but it turns out that this top reaction right here has a double arrow, and you might have noticed that, you might not have. The previous reaction has an intermediate as the only product of a reversible reaction, which we'll learn about in a little bit more in a couple of weeks. What that means is the rate of formation, how quickly you make N2O2, is based on how quickly you use up the NO. In this case, it's a 2-to-1 ratio. So for every 1 N2O2 I make, I use up 2 NO molecules. And of course, we know that stoichiometrically, but you can make the same claim kinetically. So this means that the rate of formation of N2O2 is equal to the rate of consumption of NO. What that means is, in brackets, N2O2 is going to be equal to NO to the second. You'll notice my color coding here, I matched up with the colors over here, because then I can do this. I can take my rate of my slowest step, which I already know is going to be the rate of the overall equation. There it is written out. There's my intermediate. Here it is again with that's causing a problem. I can use this relationship from the previous step, because it's reversible, I can use this relationship and I can substitute in. I can just do some algebra. Get rid of the n2o to the first, replace it with no to the second, and this right here, right there, bottom center, k no to the second, o2 to the first, is my rate law for the entire, for the overall equation based upon that mechanism, based upon the slow step and the fact that we have an intermediate in that slow step. Here's a couple of examples that I pulled from the web. Sorry about the quality of these, but there's two mechanisms on this slide. In this case, we're making x, and then we see x again in the slow RDS, rate determining step. So a to the first, x to the first is going to be my rate law expression for that step, but of course x is not found in my overall equation. If you add them together, you'll notice x is an intermediate. But because the previous step is reversible, x to the first must be equal to a to the first, b to the first. So when you combine that all together, a to the first, b to the first, multiplied by another a to the first, you get a to the second and b to the first. Here they're saying rate is directly proportional to, but we can say equals to k times a to the second, b to the first. Same idea down here. There's my slow step. It's the rate determining step. It's going to be step 2. It contains a2, which again is another intermediate, so we can substitute in and replace it with a to the first, which of course we can collapse, combine, and call it a to the second. Last slide here. I wanted to show you here that the slow step, the rate determining step, is the first one. So we're going to have a to the first, or in other words, a to the second. When you add these two equations together, the intermediate drops out, and it's not found anywhere in that rate law expression that I came up with for this step. So just because it's a double arrow, don't think that you suddenly have to do some sort of funky algebra. Not necessarily. If your slow step, which is accounted for here, includes only substances that are found in your overall equation and no intermediates, there's no intermediates in this rate law expression, so you don't have to do any sort of little algebraic equality. It can stand alone how it is.